Yeah. And it's like,
I'd like to say something about the homeworks as they come up. So here's a look at your first kind of, don't forget, you all do have a homework due today. I hope it's not too taxing. Here's the first kind of real in the trenches homework. Now, don't get discouraged too, because even though this homework is over stuff that is more elementary that you've probably seen before, properties of the integers, I think that you will find that actually it's one of the, it's kind of hard to get through this one a little bit because some of these properties are a little bit subtle. We start with these basic things that you might have, some of you might have seen in 3190, basic properties of the integers that are going to be behind a lot of the stuff we do in abstract algebra. Just these basic properties of the integers tend to govern a lot of stuff. So let's look at these problems. Suppose K, M, and N are all non-zero integers. GCD, greatest common divisor. You all are familiar with this. The greatest common divisor of two integers. Show that the greatest common divisor of two integers is a linear combination of the two integers that it's the greatest common divisor of. So in other words, show that if D is the greatest common divisor of M and N, then you can find two other integers, A and B, such that AM plus BN is D, right? So for example, this is a non-trivial result, right? Can somebody tell me what is the greatest common divisor of, oh, so we'll do a gut check on this. What is the greatest common divisor of, say, 30 and 35? Did I figure that one out for me? That's right. 5 is the great. 5 divides 30. 5 divides 35, and it's the greatest, right? I'm going to give you a strict definition of greatest. You think of this as biggest, but there's a better definition we'll get to later. Now, that means by this problem that 5 is a linear combination of 30 and 35. Anybody see how to do that? How about -1 times 30 plus 35, right? Well, that was easy. What's the greatest common divisor of 101 and 103? Both of those numbers are prime. So the greatest common divisor is 1. 1 is a linear combination of 101 and 103. That one's a little bit less obvious, isn't it? How do you do that? Well, this problem shows that you always can. Number B, show that if the greatest common divisor of K and M is 1, and the greatest common divisor of K and N is also 1, then the greatest common divisor of K and M times N is also 1. So you can't pick up any extra divisors by multiplying these two. Show that if the greatest common divisor of K and M is 1, and K divides MN, then K is forced to divide N. Right? So these are basic properties of greatest common divisors in the integers, and like I said, we're going to use it a lot. This is one that some of you may have seen, or at least around the campfire, folklore or something. Let M and N be positive integers. Let D be the greatest common divisor of M and N, and L the least common multiple. Show that the M times N is the greatest common divisor of M and N times the least common multiple of M and N. This is also very important. The next problem, we talk about sets. So I alluded to this a little bit last time. Show that if squiggle is an equivalence relation on S, then the set of equivalence classes under squiggle forms a partition of the set S. And number B, show that if PI is a partition of S, then there is an equivalence relation, which we'll call squiggle, such that the sets PI are precisely the distinct equivalence classes of S under the equivalence relation. And actually, I gave you a hint on this one last time. If you look back at the notes or the video or whatever. And finally, the infamous Chinese remainder theorem. This actually comes from old folklore that they used to, the Chinese army used to do this to count troops after a battle kind of thing. This is also very important in algebra as well, coding theory, things like this. Suppose that if you have N1, N2 up to Nk, and this is a collection of pairwise relatively prime positive integers, that means that any two of these, if they're different, their greatest common divisor is 1. Suppose capital N is the product of these. Show the system of congruences has a unique solution Z between 0 and N minus 1. And this notation here, X is equivalent to A mod N, means that X minus A is divisible by N. So anyway, so that's the warm-up problems. I think that think about these problems, because even though these are elementary properties of the integers you may have seen before, I think this is kind of a steep learning curve beginning to this. I think the next problem set might be a little easier. Okay, any questions on that? Okay. So the last thing we were talking about, the last thing I brought up was this notion of divisibility. What does it mean for one integer to divide another one? Recall that if A and B are integers, I say A is not 0 in the notes because I guess I was lazy there, but you don't need this. We say A divides B if there's a C in the integer such that B is AC. So let me ask you this. Is it possible for 0 to divide a number, right? This is one of the things you've heard in high school. Oh, you can't divide by 0. That's a big no-no. But according to this definition, can you? You actually can. 0 does divide a number, but if 0 divides a number, what does that number have to be?
0.
It has to be 0, right? So by this definition, 0 divides 0, because certainly if B is 0 and A is 0, this equation balances, no matter what C is. Everybody agree? See, that's really the point with dividing by 0, because C can be anything. So if you were trying to write the fraction B over A, you don't know what this answer is because it can be anything from one point of view. Let me give you I'm going to put this in proposition here. Some of this, in fact, I think a good deal of the stuff you've seen before. Suppose we have Z as the integers, of course. Number 1, of course, by Z plus, I could write that as the natural numbers. Anybody know there's an important fact about if you have a non-empty subset of the positive integers or a non-empty subset of the natural numbers? Anybody know what's true about this set?
Smallest element.
It has a smallest element. That is a very important property of this. And you may have seen in 3190 that this is actually equivalent to mathematical induction. That A, B, C be non-zero, then there exists a D in Z such that D divides A and D divides B. So I can find something that divides both of these. And if there exists D prime in Z such that D prime divides A and D prime divides B, then D prime divides D. And this mysterious D is called the greatest common divisor. Now, usually you all are used to thinking probably of greatest common divisors as biggest in the sense of it's the largest number. You need to think of greatest in terms of division, right? So what it means to be a greatest common divisor is it divides both A and B. That's the common divisor part. And if you can find any other common divisor must divide it. Right, and that's the greatest part. It means every other thing that divides both A and B must divide D itself. 3, given A, B, and Z, non-zero, there exists, I'm going to call this L and Z. This is called the least common multiple. Now, what do you suppose it means to be the least common multiple? Well, if it's going to be the least common multiple, it better be a common multiple. Otherwise, I've got a crappy definition here. So L has to be a common multiple of A and B. That is to say, such that A divides L and B divides L. So L is a multiple of A and L is a multiple of B. And if M is any other common multiple, then anybody want to guess what happens here? The greatest common divisor had to be divisible by any other common divisor, right? The least common multiple has to divide any other common multiple. So it's sort of like the mirror image of this problem. Well, number 4, if D is GCD of AB and L is LCM of AB, then DL is AB. That's one of the homework problems for next week. Here's another one. Let's let A and B be non-zero. Then there exists Q and R in Z. Such that B equals QA plus R. And anybody know what condition I can force R to have? So suppose I divide, I don't know, suppose I divide 19 by 5, like I was in grade school, I just divide it up, and I say, oh, it's got remainder 9. What would you say? Would you criticize me for saying when I divided 19 by 5, I got remainder 9? What's it now?
9 is greater than 5.
Right. I mean, if you're in grade school, somebody would come smack your wrist with a ruler or something like this, right? Because the remainder is supposed to be less than what you divided by, right? That's what's going on here. Well, so I guess I could have written it this way. So really, this is all this is saying. This is all this result's saying. This is called the Euclidean algorithm. If I have two non-zero integers, A and B, I can divide A into B. Quotient is Q, and my remainder is whatever it should be less than what I divided by, right? That's all this is saying here. Any questions so far? Number 6, if the so this is also a homework problem, since the greatest common divisor of A and B is a linear combination of A and B. And finally, we'll do the fundamental theorem of arithmetic. Has anybody ever heard of fundamental theorem of arithmetic in those terms? Yes. So what it basically says is many numbers you can factor different ways. 36 is 6 times 6, it's 4 times 9, it's 2 times 18. But if you factor it down into its smallest terms, there's only one way to do it. 36 is 2 times 2 times 3 times 3, and that's it. So the statement is this. You can state this more generally, but this will be good to warm up. Then N is uniquely a product of prime and here temporarily say P bigger than 1 is prime if the only positive divisors P are so. So a prime number is something that is bigger than 1. This is a temporary definition. This isn't really the best definition of a prime, but as we get more into the algebra, we'll explore this later. But for right now, we'll say a prime number is a number that's at least 2, and its only divisors are itself and 1. How many of you have heard this definition before? Prime number. Okay. Okay, any questions on that? Okay, let me give you a motivating example. And I'm going to use this. Hopefully, what I'm going to do in this example will help you with the homework problem we talked about, Chinese remainder. So here's my example. And hopefully this potentially illustrates the historic where this comes from. You have an army of 2,000 soldiers. Okay, so that's what you started with going into battle. So you had this terrible battle, and after the battle, of course, you need to know how many soldiers I've got left over, right? And you want to do this quick because the gates of Mordor are opening. So what you do is you organize your remaining soldiers into groups of 25. So here's what you do. 25 is a nice square, so they're just getting a box 5 by 5. So you say, okay, get in a group of 25. Of 25. there are 5 left over. So you see, when they all get in their boxes of 25, you got 5 people that got nowhere to go, right? And then you tell them to get in groups of 81, and there's 4 stragglers. How many soldiers you got? It's amazing that just this, you tell them, okay, get in a box 5 by 5, and they all do. 5 people say, we don't know where to go. So you write down 5. Say, okay, get me groups of 9 by 9. They do that. You have 4 people left over. That information will tell you how many soldiers you have left over. Let's see if we can figure it out. Okay, so let's start very naively. What does this tell me here? In groups of 81, so let's let n equal the number of soldiers. This is what we're trying to find out. What does that second thing tell me? When they get in groups of 81, you got 4 left over. Can somebody interpret that for me?
We have a remainder of 4.
Okay, good. I got a remainder of 4. So the number of soldiers should be 4 plus something. You fill in the blank there. That's right. However many boxes of those 9 by 9s there were, right? So we'll say 81A, something like that, right? Everybody agree with that? Okay, let's rip this off on the next one. What does the first thing tell us? Agree with that? And there's something else important.
Less than 2,000?
Unless babies were born on the battlefield, this has to be less than or equal to 2,000. Everybody agree with it? Of course, that's an important restriction as well. Okay, let me start off very naive. Maybe I've only got 4 left, but that's clearly impossible. Why? Because I've got, there has to be at least 5, right? Okay, maybe it's not 4. What's the next possibility here? I guess 85, right? Well, let me write down the next couple of possibilities. 166, 247, and 328. 409 and 490. Et cetera, et cetera. All right, if I agree with my addition there. And it keeps going. So I could make a list up to 2,000, which I'd rather not do, right? I don't think anybody wants to do that. It's not terrible, but I'd just rather not. But whatever answer I get, I mean, right out, it can't be 166. It can't be 247. Anybody know why?
The second equation.
There's no way it works on the second equation because guess what? What do you know about the second one? That is correct. This one right here tells me that no matter what, the number of soldiers I have left have to be divisible by 5, right? So my only chance is this. And then look, 4, let's see, that's that one works. Can anybody pick up a pattern here? So what's gonna happen here? The next 81, let's see, I guess I get 571, 652, 733. I already grow weary of this. Can anybody predict when's the next? So notice these aren't gonna work either because they're not divisible by 5, right? But notice these end in 6, 7, 8, 9, 0, 1, 2, 3. Anybody want to predict when's the next possibility, multiple of 5?
From the previous
Okay, good. How much do we jump here? 405, it looks like. So the possibilities are 85, 490, because it jumps 405. The next one should be 895. The next one should be 1300, I guess. The next one should be 1705. And the next one should be 2110. Oops, already too big. So we've got those possibilities. Everybody agree with it? Which one is it? Notice all of these work for this equation, but the only thing they have in common here is they're divisible by 5, really? So can anybody tell me which one of these, when you subtract 5, so what does it mean to satisfy this equation? It means that n minus 5 is a multiple of 25. When you subtract 5 from this, is it a multiple of 25? When you subtract 5 from this, subtract 5 from this, subtract 5. What about that one? 1,705 soldiers left. Now, any of you that think that that's cumbersome, remember, while I was doing this, I was also teaching it, A, and B, I challenge you to count to 1,705. Now I challenge you to do that with an army that just had like swords stuck in their legs and stuff, right? You're not going to get a good count on that, right? This was very, very fast. 1,705 out of the 2,000 are still there just from using this little theorem, which is kind of cool beans if you ask me. So let me give you the statement of it. And again, you can see this in your homework. Of Chinese remainder theorem. And in this class, CRT means Chinese remainder theorem and not something that can get me in trouble politically, right? So let's not go there. Suppose that if N1 up to NK is a collection of pairwise relatively prime integers. And just for the sake of clarity, this means that GCD of NI and NJ is 1 if the NI and NJ are different, right? So it just means there's no common factor other than 1 between a pair of these. And N is equal to the product of these. Then the system of congruence is X is equivalent to A1 mod M1. X is equivalent to A2 mod N2. All the way down to X is equivalent to AK mod NK. Has a unique solution, which we will call Z, between 0 and n-1. So what I'm saying here is between the numbers 0 and n-1, there is a solution to this, and there's only one, right? In fact, between every interval of this size, there will be one solution. Okay, any questions so far? The example, of course, that we just did in class, we had, what did we have? We had N1 was 25, N2 was 81, K is 2, because there were only 2 of them. And A1 was 4, and A2 was 5. That was a special case instead. Let me ask you this. Let me give you kind of another example here. I want to say something briefly about modular arithmetic. How many of you have ever seen or played around with modular arithmetic? Has anybody ever? It's okay if you have, right? That's what I'm here for. Well, this is, when you see this notation, which you might see written this way, or sometimes this way, is you just take the numbers from 0 up to n-1. So for example, Z5 is 0, 1, 2, 3, 4. Now, this is a really cool thing, and it's kind of a first example that I'll refer back to when we first start talking about proofs. I would specifically at Z5 probably first. This is basically a structure where actually you can both add and multiply. Now, A bar plus B bar plus B bar, and A bar B bar equals AB bar. Now, this is really fast and loose of me to do to you right here, so I'm going to do some examples to kind of, because what do I mean by A plus B bar? All right, so example, in the example, so what would 1 bar plus 2 bar be in Z5? Well, 3 bar, right? I know what 1 plus 2 is. Everybody okay with it? Here's where I get a little kind of worried here. Well, by what I wrote over there, this should be 7 bar. Oh, and now I'm angry because look at my list of Z5. There's no 7 bar. Oh dear, what do I do? Anybody? Yes, that's right. Think of it like a clock. Let's see, what did I have here? 4. Now I add another 4 bar to it. 1, 2, 3, 4. This is 2 bar. And that's exactly what she prescribed, right? You basically just subtracted the 5 off of this, right? This is Z5. Here's the rule is what you do is you take whatever A plus B is, which is 7, and use that thing that we talked about earlier. Divide 7 by 5 because it's 5 bar, and the answer should be the remainder, right? So, in Z5, say, 126, 1267 bar is equal to what? If I added up so many things that I had a 1,267 under the bar, and Z5, what should this be? This is also 2 bar. Because if I divide this by 5, I will get remainder 2. Am I okay with that? And another way you can think about this is like a clock, right? If it is 10 a.m., what time will it be 4 hours later?
2 p.m.
That is correct. Unless you're in the military, it's not going to be 1,400 hours. It will be 2 o'clock. What did we do? We took 10 p.m. and then you counted 4 up. 11, 12, 1, 2, right? The 12 is like the 0 starting over. That's what we did here. 3 bar plus 4 bar, 1, 2, 3, 4. It's this. Or 4 bar plus 3 bar, 1, 2, 3, 2 bar. But if it's a big number, just divide it by whatever this is and take the remainder. Everybody okay with that? And the multiplication works the same way in the following sense. In Z5, 2 bar times 2 bar is 4 bar. Everybody okay with that? Well, that was easy. I didn't have to go around, right? By the way, everybody notice that's minus 1 bar? Everybody okay with that? Because subtract 5, it's the same thing. How many of you believe in imaginary numbers? Oh, everybody, that is such a horrible terminology. Natural number or imaginary numbers. And here's one right here. In this structure right here, when I square 2, I get -1. Everybody okay with that? But how about something more exotic? Bar again. Well, this is 42 times 3, 126. Same principle holds there. Everybody okay? You can have weird things happen too. Let's look at Z6, right? Oh, what could possibly be different? I just changed one number here, 6. But you have a weird thing that happens here. Maybe you're not used to. Notice 0 is just like an ordinary 0. What's the big thing about 0 in the integers? When you add 0 to anything, it leaves it alone, right? 0 plus anything, nothing changes. Same with this 0 bar. Everybody agree with that? In the integers, if I say A times B is 0, what do you know? One of those animals has to be 0. Agreed? Not here. You can actually, in this one, multiply 2 non-zero numbers and get 0, which is weird. Notice you should convince yourself that this can happen here, but in Z5, that doesn't happen. If A times B equals 0 in Z5, then one of those two has to be 0. A times B can be 0 here without either one of them being 0. Do you know what sets that apart? Yes, ma'am.
Oh, I was just gonna ask that of why it doesn't work in Z5, but it works.
That is a very prime question to ask. It is because 5 is prime. And in fact, if you look at any Z mod P, it will have the property that A times B is 0 means one of them has to be 0. And if you have anything that's not prime, it'll have some screwed up example like this. Okay, any questions on that? Let me give you this. How many of you have ever heard of the Euler phi function? This will come up in algebra some, it'll come up in number theory. Basically what it does is in Zn, it counts the number of elements in Zn that are units. Let me give you the definition and I'll make that more precise. Definition. Suppose n bigger than 1 is a natural number. Suppose I have a natural number that's bigger than 1. What do I know about a natural number bigger than 1? I can factor it into primes, right? Let me see. How about this? We know this is unique by the fundamental theorem of arithmetic. And again, so these are different primes. Each PI and PJ are different primes. Then this should be the product I equals 1 to K of P to the AI minus 1 PI. So I've just told you what it is. Let me do a computation and show you what's going on here. So actually, yes. Let's look at phi of 12. Well, the first thing I have to do to make this work is I need to write this in terms of 12 in terms of its unique prime factorization, which is 2 squared times 3. According to this formula, this is the product, I equals 1 to 2 of PI to the AI minus 1, PI minus 1. So this is P1 to the A1 minus 1, P1 minus 1 times P2 to the A2 minus 1, P2 minus 1. And here P1 is 2 and P2 is 3. So this should be 2 to the 1 power, because the exponent there is also 2, times 2 minus 1, which is 1, times 3 to the 0 power, because the exponent here is 1, times 3 minus 1. So that's a 1, and that's a 1, that's a 2, and that's a 2, so I get 4. So the Euler phi function was 4. What is that doing? We give you a list of numbers here. I guess I'll start. Well, no, start. What the Euler, let's count just in this list of numbers. So that's the numbers between 0 and 12, not including 12. I want to count how many of those things are relatively prime to 12. So it's got no factor in common with 12. Which one? Well, one for sure. The only factor that one has in common with 12 is 1 itself, right? What else? Yep. 5, 2, 3, and 4 right out, right? Those don't work. How about next?
7.
Oh. And 11. Notice this has got a factor of 2, 3, 2, 2 and 3, 2, 3, 2, and whatever you want, right? So they've all got factors in common with 12. Notice there are 4 of these. That's what this function does. It counts the number of integers between 0 and n minus 1, or between 1 and n, whichever way you want to do, that are relatively prime to that number. Right? And this is actually very important because these are actually the only numbers. So the significance of this is as follows. You remember the example I did with Z6. Imagine that this is Z12. And put the bars over it. Notice 2 is not 0, right? But 2 times 6 is 0. 3 is not 0, but 3 times 4 is 0 because it's 12, right? You can check all these ones that aren't circled, and there's something that multiplies by it that gives you 0. It's not 0. On the other hand, these are nice in the sense that when you multiply, each one of these has an inverse. What do I mean by that? I mean, if you look at 5 times 5, that's 25. Mod 12 is 1. So 5 is its own inverse. Same with 7 times 7, it's 49. Mod 12 is 1. And this is -1. So 11 times 11 is 121. Mod 12 is 1. So what the Euler phi function does is it counts by counting the number of between 0 and n minus 1 that are relatively prime. It counts. Basically, it's counting the number of elements that are invertible in that sense, that have an inverse. And what's left over have that weird property that you can multiply non-zero thing. It's 0. Okay. I'm going to give you one last problem, and this will free us up on Monday. We'll start groups. I'm going to give you this last kind of list of things here. Properties of modular arithmetic and some important offshoots of it. So, theorem 111. The relation equivalence mod n is reflexive, symmetric, and transitive. So it is an equivalence relation. In addition, we have the following properties. Number 1, if A is equivalent to B mod n, then A plus K is equivalent to, and let me remind you that we say X is equivalent to Y mod n if and only if X minus Y is divisible by n. And that's what I was doing like in Z5 when 2 is the same thing as 7, which is the same thing as 12 and so forth. Okay. Mod n. Well, okay, let's see. Two if A is equivalent to B mod N, then AK is equivalent to BK mod N for all K and Z. 3. This is more general. If A is equivalent to B mod N, then F of A is equivalent to F of B mod N for all polynomials. F of X, coefficients of Z. Or, and here's kind of the interesting properties. If GCD of A begins the greatest common divisor of A and N is 1. And it's 1. And X is equivalent to Y mod phi of N, not N, but phi of N, the Euler phi function. And this one's actually important in coding theory as well. Then A to the X is equivalent to A to the Y mod N. If GCD of AN is 1, then there is a unique solution. Then AC, there exists an A. There's a C and C such that AC is equivalent to 1 mod N. This is what we talked about with C12 a little bit. And in this case, and this solution is unique. Mod N. Number 6. Fermat's little theorem. I know that I know we're 2 minutes over. If you got to go, I totally get it. I'm going to write these next 3 down. You can see it on the recording, but for continuity session, you can hear. Fermat's little theorem. If P is a prime,
Polys?
and
Do you hear that sense?
GCD.
That's where I am.
A, and
Okay.
A to the P minus 1 over 1 minus C. Oh.
Oh, wow. No, tolerates. Hold on.
If A is 1,
I got it. I took one for. I didn't even get 3. But I watched them.
then A to the phi of N is equivalent to 1.
Is that A and S? 4? Did you get 3?
And finally, and I'll answer your question,
Yeah.
Uh,
The next line has it.
P is prime if and only if P minus 1 factorial is equivalent to minus prime. This is called Euler's theorem, number 7, and the last one's called Wilson's theorem. Okay, what was your question about the,
4 is it A and N is in GCD?
I'm sorry, that's an N, yes, yeah, A-N. Other questions? Yes,
What is the poly?
polynomials.
So that's what.
Yeah, sorry about that.
EA?
No, D does not divide A.
Nice.
Five is such. Oh, yeah.
Are you ready? Yeah, I'm just gonna be late.
That's the income point.
Right.
That's negative one.
Exodus.
The other ones are ones. Use. I'm listening.